Very kind introduction. So this is basically what you just said. So maybe I can skip the slide. Basically, I started in biotechnology, then I started moving to a more dark side, the IT side. So bachelor's degree in bioinformatics, then I did a PhD in experimental pathology, which was actually data management for a couple of European projects. And then I joined the technical services at EBI-EMBL, and I work in the technology and science integration team, which is a kind of a new team that started 2 years ago, and is looking at new technologies and how that can be used within the EBI, clouds being one of them, of course. Who's paying my salary? EBI again. I don't think you need an introduction to this, but anyway, we are basically the Europe main supplier for archives and services for life sciences. We're part of EMBL, the European Molecular Biology Laboratory, which is not that far away from here in Heidelberg. We have a bit more than 600 members now from 57 nations. I think is a very good achievement with Brexit around. And we're also home of the ELIXIR technical hub Tommy was talking to you about yesterday. So you all know what bioinformatics is, right? So it's the science of storing, retrieving, and analyzing large amounts of biological information. Of course, from a very low point of view, EBI can be seen as a massive number of these. So our drives are north of 100 petabytes now, packed into a reasonable, well, maybe not so reasonable number of those. This is our storage system. This is our data center in Kingston. And access quite a few of these. These are all the blades that made up the cluster, well, the several cluster we have around, which tops up to other big number, I think, 50,000 cores. However, it may seem quite a lot, but on top of that 100 petabytes, what we provide is this very huge long list of services are based on that. So, and the integration between those services is quite remarkable, I think. So part of this is actually done with clouds. We have a Vmware Cloud, more than one actually, with 40 hypervisors. We're managing 2,400 VMs with that. And this is basically the bulk of our web servers, databases, this kind of things. And then we have what we call the Embassy Cloud, which is more for research. We have some groups that are moving there for do web stuff, but not so much. It's an OpenStack cloud. It's managed and operated by EBI, 92 compute nodes. We have 6,000 vCPUs now. It's going to be 11,000 by October this year. 4 GB of RAM per vCPU, plenty of networks to go back to both the internet and the storage networks. And we have 2 petabytes of NFS ISODON, so normal NFS access. 2 petabytes of object storage. This is exposed as S3, so basically the standard in object storage around. And then we have 600 terabytes of Cinder volume, so plenty of stuff to play with. Not so easy though, again, because we have the usual big data problem. So this is a plot of different types of data we store, and of course demand is going up quite quickly, especially in genomes. Just this one. Especially because this is the amount of storage we're putting in at the EBI. It's a bit of an old plot, I'm sorry about that, but I don't think we have a new one. So we're not growing storage capacity at the same speed, which may be a problem in a couple of years. But also, as you know, we provide services, and we also have the big usage problem. So this is the web hits on our services in the starting 2012, now 2017. You see this beautiful peak here, which means we're a bit under stress at the EBI now. So something needs to change, because it's also very, there is a conference in 3 days. Everybody's trying to query the services because they want to put the abstract in, that kind of thing. So that peaks. So of course, the solution here comes the cloud. But let's take a step back and look at clouds more. Not in the EBI way at the moment, just more generically. So this is a question for you. Do you know why clouds are called clouds? Any idea? Everybody's talking about clouds, but this is kind of a fundamental question. Okay. The clouds are called clouds because since the beginning, when people were drawing architectural stuff for networks and things, the internet was drawn as a cloud. So moving from that, since the cloud is computed somewhere else across a network, clouds are called clouds. And the real moment in which cloud has been used for real for the first time was in 9th of August 2006 by Eric Schmidt, which was back at that time the CEO of Google, so kind of important person. And it says, what's interesting is that there is an emerging new model. It starts with the premise that the data service and architecture should be on servers. We call it cloud computing. They should be in a cloud somewhere. So by definition, somewhere else. A bit of history. There was actually somebody that went back and tried to find when cloud computing as a word was used for the first time. It was actually quite back in time, 1996, in a compact queue business plan. Nobody knows why it was there, but it was kind of cloud computing, a bit different, a bit more internal, if you want. Then March 2006, AWS console line. So this is the Amazon service. Early 2008, so between here, Eric Schmidt said that thing. Early 2008, NASA releases OpenNebula, which is the first, basically, open source cloud out there, which is kind of not so healthy now, but anyway. February 2010, Azure comes online. This is the Microsoft offering. They got it wrong. They're rebranding everything now. It's much better. July 2010, NASA and Rackspace kick off the OpenStack adventure, which is now, OpenStack is what you were using yesterday for the practicals, and this is now basically the de facto standard for open source clouds out there. May 2012, Google joins the party with Google Compute Engine in preview, went general availability in December 2013. So it sped up quite a lot. Has somebody explained you the difference of these three things? Private cloud, public cloud, and hybrid cloud? No? Okay. So private cloud is a cloud that is operated by an institution for its own means. It's very flexible, so that the cloud you were using yesterday was in part private, right? I think we discussed this. Okay. It's also CERN is basically has the biggest deployment of OpenStack in research. Is a mind-blowing 200,000 vCPU deployment that is scattered across actually 2 data centers in 2 different European countries linked by 2 100 gigabits dark fiber paths. This is still private because it's only accessible from inside of CERN. A public cloud is something that somebody managed for somebody else. So EBI is managing Embassy, which is a public cloud, and people from across the world can come and use it. Hybrid cloud. So the guys here, these are the 2 guys that actually came up with the definitions, not my stuff. They said is a composition of 2 or more clouds. I would expand this with a composition of your own data center, so the physical one you have, and a cloud. And this unlocks very nice things because you can use cloud resources along with your own data center. It's very good in coping with peaks. So the reason why EBI started looking at clouds is because as data increases, we want to have the community bring their compute to data, because usually compute, which means all the pipelines, all the code you need to do your stuff, is usually much smaller than the data now. Time Cancer, and I think Sergey will tell you about that something today in the afternoon, had 1 petabyte of data, and the compute was a few megabytes, I think. So it's much easier. That's the reason why we have Embassy Cloud, because that's sitting in London, close to our archives. But hopefully, you will not bring all your compute to our data center, because that will be a bit of a long queue. So what we're planning to do is push relevant data sets and services out to cloud providers. Of course, EBI, Embassy Cloud is the first step. ELIXIR, what Tommy was saying yesterday, has a compute platform that will start delivering, well, it's already delivering kind of a bit of compute. European Open Science Cloud will come online and provide services across Europe at some point. And then, of course, last iteration, AWS, GCP, Microsoft Azure, so the public clouds. What's going to come after that, we don't know yet. And we're looking at hybrid especially because it will help us optimize EMBL-EBI Capex versus Opex. Raise your hand if you know what Capex and Opex means. Okay, more or less. So Capex is capital expenditure, so that the money you spend buying hardware and putting it into your data center. Opex is the money you pay to operate it. Of course, if you can use clouds to supply your own, to help your data center to cope with the load, you can basically let Capex, so the money you spend putting hardware in, lag behind the demand, and use Opex to cope with peaks. So we don't need anymore to size the cluster of the EBI to cope with the massive peak we had 3 days before the conference, but we can just spin up workers in the cloud, then get rid of that. So the key point is here is how to make data and workloads fly to the cloud, right? And in reality, we are looking at a multi-cloud hybrid approach because we don't want to be locked into something, right? And the reasons why we're doing this is because long-term storage in the cloud can be expensive, especially if you talk about block storage. You get a nice bill if you try to store a petabyte for a couple of months in the cloud. And because of our mission, we will need to keep a custodial copy anyway. So there's no point in time in the future where EBI will copy everything in the cloud and get rid of the storage. We want to avoid cloud lock-in because if Amazon raises the price 4 times in 3 months, then we don't want to run stuff in Amazon anymore. So it's basically a way to say we want to move workloads where it's cheaper to run them, which could be Cloud 1 today, Cloud 2 in a week, Cloud 3 in a couple of months. And the key factor is being able to run the same workload both on-prem and in the cloud, because that gives you the flexibility to do basically whatever you want. So clouds now boarding. This was how we boarded the EBI in clouds. So in the last 2 years, my team was established, first of all, and then we established an EMBL-EBI benchmarking suite. This is a very silly, if you want, bash script that we can run in different VMs across different clouds to monitor what's the performance of the VM itself, the network connection back to us, these kind of things. So we can compare across the board. We've been running basics and now advanced proof of concept with several cloud providers, AWS, GCP, Azure, we got them all. UK-based cloud providers were also tested. And the advanced proof of concept actually started in, well, the process started in summer 2016 when we issued the first EMBL-EBI cloud tender, which was a bit painful to write. Shortly after that, September 2016, TSC, so the technical services at the EBI, started what we call the Ebi Cloud Working Group, which looked at clouds in many different ways. May 2017, so a few weeks ago, if you want, the first results came out of the many pilots. A few more words on this. So we went out with the tender subdivided in 3 lots because we wanted to have something OpenStack compatible to go along with our Embassy Cloud, something VMware compatible because we wanted to do disaster recovery, and scale, what we call scale out, so just raw compute. Give me CPUs and storage, I want to crunch numbers. Okay. This scale out was run by GCP and Microsoft Azure, the other 2 by a UK cloud provider, which is UK Cloud. So on top of those resources, we started several projects that cover basically 3 different things. So how to run science in the clouds. So absolutely independent workloads running there. How to extend our data center in the clouds. This means we want to have a copy of a database in the cloud that keeps sync. We want to have some worker nodes linked back to our LSF on-prem. And disaster recovery. So if something strikes the data center in London, we can spin up a new EBI somewhere else. Or if there is a thunderstorm like yesterday and the cooling in the data center in Kingston goes off. It was fun. But anyway, let's stop with the business stuff and go back to science. So what we learned is that there are basically 2 different possible approaches to port pipelines to the cloud. The first one is mimic your on-site infrastructure. So you basically deploy a batch system with a shared storage because you want to have NFS across, right? You run your workload. As soon as you're done, you bring your data back, so the results come back to your own data center and you kill everything. Done. You don't pay anything anymore. The second one is use cloud-native stuff. So that allows you to do things like auto-scaling, using object storage, and optimize for the cloud, which is rather important. So So of course, the two approaches, they both have some good and bads, right? So the good with mimicking your on-site infrastructure is it's easy to start with, right? Because it doesn't, what's this? Sorry about that. It doesn't require too many changes to your original pipeline. You're running it into a batch system in your institute. You're running it into a batch system in the cloud. It's reusable because once you come up with the deployment of a cluster, you can reuse it for multiple pipelines. And to some extent, it moves the burden from science to IT, because the IT department at EBI had to come up with the deployment of an open lava cluster in the cloud. And it's also very nice to do bottleneck detections, because you can run your pipeline in a cluster that is fully dedicated to you with nothing else going on. And you can monitor what's happening. So that's very nice to pin down why your pipeline is going slow. And you still have Posix. Raise your hand if you know what Posix is. Oh, okay. Well, basically, Posix is the standard that lets you do LS on a folder in a file system, okay, which can be very important. The bad thing is it's way less cloud efficient, so you end up with higher cost, reduced output, and reduced performances. Cloud native paradigms. The good thing is, well, if you start using object storage, auto-scaling, all those cool things, in the end you have a higher throughput, higher performances, and lower costs, because you're using stuff that is meant to run in the cloud. You're not forcing the cloud to run stuff it was designed basically 50 years ago to run in the data center. It's bad because it's more complex to start with, because not finding a nice batch system in the cloud anymore. It may not be suitable for all. There's no Posix, so if your tool needs Posix, maybe you may have some issues here. And it requires changes to the pipeline. So this means you need to go in and change the way you do stuff. So what is going to come next is the mighty history of the marine metagenomics pipeline. Sorry about the thing, but it was, which is a pipeline that is at EBI at the moment slowed down because it has very high ops. It's very high ops demanding, and we need to slow it down because we want to keep the storage alive. So how all of this started is with a massive ops, which was actually, oops, we need more compute, because the amount of data that gets submitting every day in the metagenomics field at the EBI is just crazy to some extent. So this is the marine metagenomics pipeline. It's actually underpinning the metagenomics service, and there's the link. And you can also find all the people that are working on this. And it was designed to run on the EMBL EBI production cluster. This is LSF. And we were forced to throttle it down, so the number of jobs they can run concurrently, because they have very high ops needs. So this is the perfect cloud offload candidate. If we can move this compute to the cloud, we can have them more happy because they can run stuff faster, and we can at the same time free resources on-prem for others to use. So the way we did this is a bit of a technical bit if you want, is basically using OpenLava, which is a fork of an old LSF, and that gives you compatibility basically between the two. And we did a very easy deployment if you want. Single master node, bunch of workers that would manage, so we could scale up and down. 3 Cinder volumes, so using OpenStack, linked back to a single NFS server that then exports storage across the nodes, and actually also the master node, so there should be a red line here. And then we made this out of magic because we wanted to deploy this as quickly as possible. So we used 2 tools to do this: Ansible, that you've been using yesterday, to do all the VMs and application configuration. And then we also used Terraform, which is a tool made by HashiCorp, which is a company you may know, is very famous in the DevOps world, to do the infrastructure provisioning. So what you were doing yesterday, 2 days ago, clicking all the buttons in the Horizon interface to spin up a VM, you can basically do it as a code with Terraform. So you can run your Terraform code, spin up the infrastructure, and then use Ansible to make a bunch of VM into a cluster that actually works. However, this is just infrastructure, right? What about the pipeline? And that's where what we call ResOps comes in, which of course ResOps is DevOps for research. Because the pipeline must be deployable on demand as compute. Because you need to keep in mind that clouds will move as the real ones, right? terms of pricing, services, stuff you want to try. And you'll likely be in a multi-cloud environment. So if you, let's say in 10 years, you run stuff at the EBI, and EBI at some point decides to move from Amazon to Google because of pricing, this is the tender way we do the stuff. You need to be able to basically redeploy short notice somewhere else. So our first steps and our first test with ResOps was basically, we went to the marine metagenomics guys and we said, okay, can you please give us the installation how to of your pipeline? And we used Ansible to do it. We failed many times, so many times, I've lost count, I think. That's okay, it's science, so it's allowed to fail, right? Because of all the hard-coded stuff that were in there. Queue names, paths to storage system that are, of course, only present at the EBI, and God knows what, because we lost track of all the things. But this is normal because, you know, for a pipeline that has been running for, say, 5 to 10 years into a data center, into a batch system on-prem, you know, you do have some strings going back to what's there. We eventually succeeded after a month, more or less. We both learned a lot, as in what the science teams need to do to board the clouds, and what we as IT, we need to provide them to make the journey easier. And in the end, we had a reproducible deployment of the pipeline. So we were able, as IT, to deploy the pipeline the same way they deploy it in the cluster, which is rather interesting, I think. So what happened next is that all of the story started before the hybrid cloud working group I showed you before, so September last year. And we wanted to try something hybrid with the marine guys because it was a pipeline that was already ported, and it was actually easier to do it instead of starting with somebody else. So the pipeline was changed a little bit in terms of how they fetch data and push data. So they don't expect anymore the data lying in a storage system. Just do a call back to an FTP server. Actually, this is a ENA FTP server to pull the data into the cloud, do the compute, and in the end, the last step of the pipeline is sending back the data to a private FTP server. Then we went on doing two things. Tested its scalability, so how much can we scale in the cloud, and test across different platforms, because we wanted to compare performances. So can we run as fast as we run on-prem? Amazon is as fast as Google, that kind of thing. And also compare costs. So what's the cost of running something in, out here, out there? So the first thing was scalability, we said, right? So this was done in our OpenStack, so Embassy Cloud. These are four ENA studies run starting from a 22 megabyte study, which is very small, to a very big, this is, well, very big, 16 gigabyte study, which is not very big, but it's big enough. So on this axis, you have the vCPUs. So these are all clusters with basically 80 cores, 160, and up twice every time. And this is the compute time, wall time. So the moment the first job was submitted to the scheduler to the moment the last one ended. Okay? As you can see, the small one didn't really take advantage of any of the additional power we put in, because the input was small enough that all the compute they needed was already here. As you go up with the size, you see you're actually cutting the compute time quite a lot. Then you always reach a plateau, so the plot goes straight, because again, the input is not big enough, so you don't need all that capacity to cope with the pipeline, which is very important in many things, and we'll see it. So what we also did was monitoring what was going on. So we basically built a program for them. And this was a bit of a very harsh wake-up call, because have you ever seen a ganglia plot before? Cool. So for those who don't, this is basically saying the red line is the number of cores we had in the cluster. This was actually the longest run we ever did in Google. There was a £2,000 price tag attached to this. Yeah, it was fun. So this is the red line is, well, you need to try, right? So the red line is the amount of CPUs we had available. The blue line is what we were really using. Kind of sucks if you want. Same thing with memory. There are almost 2.5 terabytes of RAM allocated here. Forget about the green one for a second. The blue one was what we were actually using. This again is a bit of a big gap. The green one is the cache. So this is the operating system caching stuff, which helps you in reads because the files are on the memory, not on storage, but, well, not so good. And all the peaks here are the network. So this is the pipeline ingesting data from DNA, FTP, and this is the pipeline sending back the results. So average utilization of the system, 20%, quite bad. And of course, the bad thing, especially when you are in public clouds where you pay, you are paying for this, right? You don't use. So that's the reason why optimization is very important. So another thing is the reason why, and that's the very bad thing, the reason why this cap was there is because according to LSF, the cluster was at capacity, full capacity. They were asking so much over-provisioning, basically, over-reserving resources that we ended up with a full cluster according to LSF and an empty cluster according to Ganglia, which of course Ganglia is right. So you need to be really careful when you move across, because something that you don't perceive the cost in your own data center because somebody else is paying the bill will strike you quite badly if you run it in the cloud and you see your credit card in it. So the second chapter is about, if you remember, going across. So what we did was taking some of the inputs, not all of them, and we did the same run in Google Cloud Platform, OpenStack, so this is our Embassy Cloud, and UK Cloud, which is a UK cloud provider that offers OpenStack. Sorry, some tables now. So again, these are the 4 ENA studies with their size, so you can also see what we did. And the first question was, can we run as fast as on-site? Because that's the question every single researcher asks, right? So this is the compute time on the cluster. So this is the EBI production cluster, Embassy Cloud, and GCP. As you can see, the 3 small ones, we actually go faster in Embassy and in GCP. This is because the cluster is basically empty there. We're not using a production system. As soon as we go up with the size, these things are queuing more jobs. The number stays low in the EBI because you have basically 50,000 cores to schedule your stuff in. It goes up quite a lot in the other ones because the cluster compared to the EBI production cluster is quite small. So you're increasing the amount of time you basically wait in the queue. That's the reason why there's this trend. Second thing, well, third, was can I have a bill, please? Because that's the other thing. So it was basically not so easy to get the cost of running a pipeline in the EBI cluster because of the way clusters and data centers are managed. We're trying to do this. It's very complex for obvious reasons because the electricity bill is paid by somebody. The hardware is bought with the EMBL funds, so it's a bit crazy. But we managed to have costs for Embassy. So at least we have a clouds versus clouds. As you can see, compute time, kind of almost there. UK Cloud seems to be a bit slower. Costs. So this is the cost of running a pipeline. This particular run of this particular pipeline in UK Cloud, GCP, and Embassy. So these two are rather close, I would say, almost in all of them. Embassy, of course, comes much cheaper. So 2 things here. The first one is it is cheaper because it's your own stuff. I also have the feeling that these numbers are some way biased in being too cheap compared to the real cost we are sustaining to run all those things because we're using storage, we're using hypervisors, so it's very complex. We're using networks. In the cloud, it's easy. You tag everything, you pull the tag, and then you know what's the cost. In your data center is a bit more complex. And then we also did ask the second question. So what is going to be the cost in the spot market? Raise your hand if you know what the spot market is. Okay. So basically, it's something that Amazon invented. And you're basically saying, okay, you bid against the price. So you say, I'm happy to pay this amount of money for this type of instance. And of course, this is a market. So many other people around the world, thousands of other people around the world are bidding in the same thing. You may have up to an 80% discount on the instance full price with doing this. The problem is you may also be terminated at short notice. This ranges from 30 seconds to 2 minutes. So you have 30 seconds, well, 2 minutes to basically checkpoint what you're doing, cut down the VM, because otherwise the cloud provider itself will just kill you off. But at the same time, 80% discount is kind of interesting, isn't it? So we did a comparison. This was only in Google, where actually the spot market is called preemptible VMs, because they don't like to use the same terms across and make our life easier. Again, running time, cost of normal VMs. This is the run I was talking to you about, £2,000. Same stuff in preemptible VMs, 500. So it can be painful to get into the spot market, because your application needs to change and cope with failure if you want. But then in terms of what you can achieve, it's quite interesting. Because the thing you can do here, assuming your input again is big enough to take advantage of the scale, you can either run at this scale and say, okay, I'm happy to pay 500 because it's better. Or you can say, okay, I want to spend £2,000 in the spot market, and that gives you back basically 4 times the compute power. Depends on what you want to do. But the real question we had, and what we call the Holy Grail, was something different. So let's assume for a second that all the 3 things are true. So your pipeline scales, you've got an input big enough to take advantage of the scale. And the strongest assumption of all of them, everything works as expected. The real question is, can we run the same workload faster, spinning up more VMs, and pay the same price that we would pay running a smaller scale for a longer time? So if we run 50 VMs for an hour, or 100 VMs for half an hour, ideally we should pay the same price in the cloud. This was something we really wanted to test, because it was a bit of a question mark for us. And the curious case of SRP 005784 gave us the answer. So this is again the same plot you saw before, number of vCPUs. So again, 80 up. Against the compute time. So let's focus on the blue one for a second. So the blue one is the compute time, wall time clock again. So as you see, the first 2 times we doubled the size of the cluster. We cut the compute time quite a lot, almost half. Okay? And then again, we go flat because the input's not big enough. So this was actually a GCP run. What we asked to GCP is we tagged everything we used with tags. Can you tell me what's the cost of the run of SRP blah, blah, blah? And we pull it out. And that's what the orange line is. So for the first 3 tests, we paid basically the same money, £20, £15, £18. But at the same time, you're cutting the compute time, what, 4 times? As soon as you lose scalability, so you're putting in additional resources you don't use, so this goes flat, the cost goes up because you're not reducing the compute time. But this is actually what we're looking for, right? So we pay the same price, and the compute time is 1/4, more or less. In other cases, they're not as curious as, this is, again, our old friend. This is the super small input, the 22 megabytes input, the one that basically didn't take advantage of scaling at all. As you can see, compute time 96. This is a 93, 96 again, so we're not gaining anything. And the cost goes up each time because, again, you're putting in resources you don't use. This is a bit of a middle ground between the two. So we did cut the compute time quite a lot. The first time we scale up the cluster, not so much the third time. And again, you see £7, £8, the first 2, so same price. And then up we go because we're not taking advantage of anything. So are you still with me? Yeah, more or less, okay. So why do we need to bother with resups? Because resources aside, so the fact that you can take advantage of compute that is sitting somewhere else and not in your overcrowded data center, is that because packaging up pipelines helps in a few things. The first one is to do some cleanup. The amount of stuff we clean in terms of dependencies, old files, and old things in this pipeline was rather remarkable because it has been there for 5, 6 years. And of course, pipelines do change, but they don't always clean after themselves. And then if you do resups, so if you deploy your pipeline with DevOps approaches, it increases reproducibility because it doesn't matter what your group deploys the pipeline, right? Because it's using code that is always the same. is possibly in a Git repo, so it's tracked. So it helps you to be consistent. And also, if you're talking about open source code, so you want to share your ResOps code with somebody else, you can have somebody on the other side of the pond in the US deploying your pipeline as you do, without you being there. And this is also very interesting when you start talking about who is paying the bill, because if you host them in your, let's say, cloud deployment or data center, you or / your institute is paying the bill. But if you give them a way to deploy the pipeline in the cloud, in their own cloud, their account, the bill is not anymore on your credit card, right? So what you can also do is pre-bake your pipeline. So what we discovered with the marine metagenomics pipeline is that it was very big. Like it took 40 minutes to deploy. And this is because they were pulling in reference data, algorithms that needed to be compiled, all those things. So what we did in the end was we deployed it once in a cinder volume, the same stuff you did yesterday or 2 days ago. We took a snapshot of it and then an image. And an image can be used to create a volume. So the moment you want to deploy your pipeline, you just need to say to Terraform, in this case, that volume is not empty. Use the content of image, blah, 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 to fill it. And that means you're not spending 40 minutes anymore, but you're spending basically 30 seconds to deploy the pipeline, which helps quite a lot. You don't have a cluster waiting for something to be installed for 40 minutes anymore, only for 20 seconds. And then you can use the Ebi Cloud Portal to support the click the green button scenario. This is something we've been working quite a lot in the last year and a half. And it's basically supporting what we call the quest for the green button. So if you have a non-ResOps bioinformatician, which doesn't basically understand a single thing about clouds and possibly deploying systems, you will always get the question, okay, can I click a button somewhere and have this stuff deployed? Because I don't want to bother with all the technicalities behind this. It's not my job. And that's the reason why we started thinking about pipeline as a service. Right? So it's not infrastructure as a service anymore, it's pipeline as a service, which is not recognized, it's just us. But, and this is a step forward, because sometimes your users or our users are low-level IT users. Okay? They're not confident with this bash prompt, let alone deploy something in the cloud where costs are attached. So that kind of scenario requires a more guided deployment, right? Something that I want just to type in a few things, number of nodes, and then you do it. And that's where the EBI Cloud Portal comes in. So the way we plan to support this at the EBI and across Europe. So what we are thinking is, what we're talking about is basically the one-click deployments to an experienced user. And it wraps around Terraform and Ansible. So at the moment, it's actually a bash script that runs Terraform and Ansible. And what you can do, as you've seen yesterday, Ansible gives you a very easy way to package up applications. And Terraform gives you the same for infrastructure. So the way your cluster is actually laid down in the cloud. And what we built was basically a REST API that you can query to do your deployments. And we also built on top of it an Angular web application. So the important thing here is everything is actually a REST API. So there's a project that is phenomenal, which I think somebody will tell you about tomorrow, that is using our REST API to do the deployment. They just have a different front end, which to some extent is much more guided. So there's really just a button there to click. And what you can do, at least using our Angular web app or the REST APIs directly, is add, deploy, and destroy application and credentials. So you can put your own cloud credentials in, and the portal does the rest. You can share them with other users and teams. So if you are the ResOps guy in your team, you can come up with the application, add it there, come up with the configuration you need to add, the cloud credentials you need to add, then share it with the rest of the team, which at that point really needs to just click a button and go off. And also support single sign-on via the ELIXIR AI. So if you have an ELIXIR AI account, you can just log it in. So the anatomy of a portal app is quite easy, I think. So it's a Git repo. We use GitHub, but whatever Git repo we can clone on the public internet is good. And then we have basically several folders. I don't have time to go into the deep here, but they're hosting the Terraform and Ansible code for deploying to OpenStack, Amazon, Google, whatever you need. Terraform now supports, I think, basically 90 or 100 different cloud providers. So. And then you have a manifest file. This is the bit portal specific if you want. It's a JSON file in which you basically say the name of the application, which cloud provider it supports, inputs, so the ENA code I want to process, outputs, I want to give you back the IP of the master node because you need to SSH into it, and a few other things. And what you get as a final result is basically a card in a website. I don't think we'll have time. No, but come and find me. I'll show you something. In the website where you actually have. This is the application I actually used to do all the testing I've seen before. It was all deployed through the portal. The name of the application, the cloud provider it supports, posted here, version, contact. We don't need volumes here. Inputs. So can you please give me the ENA code you want to process, the number of nodes you want to use? And these two are just a way to shape how many runs we want to run at the same time, because an ENA study can be made of multiple runs. I'm sure you know better than me. And then you just click the button and the portal deploys it. You'll be able to see it by saying starting here, running. The interesting thing about this application is that it's not just deploying infrastructure, it's actually running the pipeline itself, because we use Ansible to fire off the first step of the pipeline. So we basically say, okay, this is the ENA code you need to process, run it, and as soon as the processing is done, you can kill the cluster with another button, or the pipeline if you want. We're also working on what we call the kill me please endpoint, which is going to be an endpoint that the cluster will be able to call to be terminated because the computer is done or there was a failure that is not able to fix. So I want to be removed because you don't want to pay money for nothing. So ResUps, my thoughts if you want. What we see, what I think is, this is going to be a big thing because everybody in bioinformatics, life sciences is talking about clouds now for several different reasons. It's a very neat figure that can basically build a bridge between science and clouds. The same stuff that a bioinformatician was 5 years ago is still now, bridging IT and life sciences. This is going to be the next bridge we need to build. And there's a huge gap in the market for this. So if you do this stuff, I'm pretty sure you'll find a job quite soon. It's not too bad to get on board. And this is an example I always use. So when we started working with the marine metagenomics team, they got very interested into Ansible because they said, okay, well, actually, it's not so bad to use it to deploy the pipeline ourselves, right? So we gave them a 2-hour introduction, very low level, the kind of stuff you did yesterday, more or less. And 2 months later, the pipeline was deployed using their code, also by us in the cloud, and in the production system of the EBI. So now there's a single Ansible script, kind of single Ansible script, that does the deployment on-prem and in the cloud. It's an Ansible role, actually, since you know what our Ansible role is now. And since they weren't happy enough, they also started looking at CWL. Raise your hand if you know what CWL is. Hi. So CWL is the new standard, the common workflow language, if I got it right, which is there to help you describe your pipeline in theory, agnostic way that you can run in different kind of systems. The only problem is that the system to run it at scale is not yet there, but so what we think ResUps are, they're most likely bioinformaticians because you need to understand what you need to run. They will most likely have some basic sysadmin skills because they need to configure systems and machines and things. They should definitely be happy to work with clouds because that's part of the definition if you want. It doesn't mean you need to be happy to work with public clouds, so where you get a bill in the end. It can also be your own OpenStack, right? You don't need to go fancy and do stuff in Google if you want. You don't want. The learning curve might be steep, but it's getting better because tools are getting better. So Ansible is quite easy. I think you managed to do basically installed packages and everything yesterday in, what was it, a couple of hours. But it's also because clouds are getting better. They offer better services, they're easy to use. There are tools like Terraform helping you anyway. And because proper training starts to pop out. Today, this workshop, this summer school, is a good example of it. We're also starting to do training at the EBI in ResOps. We started a month ago, and we had to add 2 dates because we were basically selling out so fast that we had to add more. So we got everything right: pipelines, data clouds, training of RevOps to do everything together. And we all go home now. All right. You know what this guy is, by the way? Exactly. This is part of the British culture, Doctor Who. So the reality is that the relationship between industry and science, which is something we try to foster as much as we can at the EBI with our industrial program, is a bit of a troublesome relationship, right? Because what it means is that there is still room for improvement, because industry is different from science. And the first customers of the clouds were industries. Because industry has different requirements. I want to sell stuff. I don't want to do science. Different strategies, the way they want to sell stuff is different from the way you want to do science. And different final results. They want to sell you the cool product they just baked against I want to publish my paper. And we need to understand each other. So this goes back to the fact that as we as EMBL IT, EMBL EBI IT, they had to talk with the science people to understand what were their requirements. And they had to talk with us to understand what we could provide them. At the same time, we need to do this talking between science institution, research institution, and cloud providers. So surprise, surprise, this is something that actually started 5 or 6 years ago with the Helix Nebula initiative, which later on gave life to this Helix Nebula, the Science Cloud, which is a pre-commercial procurement. I'll tell you everything about this in a second, where basically many procurers, EMBL, CERN, most of them, Sarah, you might know that one, committed procurement funds. So we put in the money, manpower for testing and evaluation, because we want to test whatever will come out of this. Use cases, because this is a kind of R&D project. So these are the use cases we want to support. Please help us doing this. And in-house IT resources, because we're talking about hybrid clouds here again. So we need to commit some of the resources we have on-prem to do the tests. And in the end, all the services that will come out of this will be made available to the public. So the total procurement budget we had across the many procurers was like 5 million, which is not a super big number, but it's also not so small. So the way a pre-commercial procurement works is R&D, if you want. So we started in January 2016, saying, okay, EMBL has these use cases, CERN has these use cases. And what we tried to do was to condense them into what is called a technical specification. So what we want in terms of performances and all those things. We went out with the tender here, so basically midway through 2016. Companies were allowed to bid against it with an idea. So this is the idea that the product we will build for you to basically comply with those specifications. 4 of them were selected. They were authorized to go on in what we call the solution design. So what they had as an idea was put on paper, okay? With as many details as they could, which was a bit disappointing in some case, but anyway. Then at the beginning of a few months ago, we started doing the prototyping, which means 3 of them were selected to go ahead. This works that way. So 4, 3, 2, and 1 winner in the end. And they started doing the prototyping. So what they're doing now, we are just here, is what they wrote on paper, they're building it. In 3 days, the initial phase of this prototyping will end, and we'll start having really resources we can use. So we will start saying, okay, this works, this doesn't work. at the end of this year, so the end of the prototyping phase, we go on what they call the pilot phase. So we'll take whatever is there and scale it up to the thousands of cores, I think. I don't remember the number, to be honest. End of 2018, whatever will come out of this as products will be available for the general uptake. So EMBL is in this with the 3 use cases. Pan cancer, again, Sergey will tell you something about this in the afternoon. And this was basically a project that computed the chunking through a petabyte of cancer data to try to understand if there were common variants among the different types of cancer. We also have EBI-EMBL, and this is about building image data repositories and tools and make them available. And we also have what we call ELIXIR long tail science, that to some extent, this is the very tricky bit, because we want to give access, to simplify and give access to people to quality control data, services, tools. Also to what we call the lone researcher, okay? The researcher that may be sitting in an office somewhere and doesn't have enough local compute power to do what he needs to do. So he needs to go somewhere else, and ELIXIR may be a way to provide this. So what we learned so far with ELIXIR Science Cloud. We're now in the prototype phase, so we're not yet at the end. It requires an interesting amount of involvement from all the parties, and this goes back to this talking between science and industry I was telling you about. But once completed, we hopefully lower the barrier for science to board the clouds, because we will have a data transparency layer, which is something that in theory we should be able to deploy on-prem and in the cloud to see our storage system across. And then only the data you actually use will get cached, which will save a bit of memory, well, storage. Federating AI, so you will be able to come to the cloud provider with your own institutional credentials across the ELIXIR AI again, and we also try to do the authorization across that. So there's a single point where everything can be managed. And procurement frameworks, because the way you want to procure cloud is not with a purchase order, right? You want to do pay-per-use, but doing that now is a bit of hell. And it's also a matter of legal stuff. So the EBI Cloud Procurement, the one I was telling you about in the beginning, it took, I think, 2 months to write it. From the moment we awarded the contracts to the moment we managed to spin up the first VM for 2 out of 3 of those cloud providers, that process took 6 months, just because there were 2 legal departments, EBI and the cloud provider ones, trying to talk and agree on what the contract should have said. So we need to get rid of that, because it's a pain. What is going to come next after EX Nebula? Well, it's actually running now to some extent, is the European Open Science Cloud. It's not a very good definition of what this thing is going to be yet, but we're exploring it in the EX pilot project. So the goals are copied straight from the website. There's 4. So make access to data easier across Europe, establish a governance and business models to do clouds, create a cross-border open innovation environment, and establishing, this is the funny one. If we manage to do this, I'll be a very happy guy. Global standards for interoperability of scientific data. This is something everybody has been trying to do in the last 50 years. So this is again use case driven. There are a total of 15 demonstrators will be selected. 10 has already been selected. And what they will do is basically state their requirements again, like Helix Nebula if you want. We need to do this. Please give us resources to do this. There will be another call that will open in August to select the last 5 ones. Feel free to apply if you want. Actually, apply if you have a very cool use case. So the way EMBL is contributing is shepherding. So there is a work package that is all about helping demonstrators board the clouds. That's what we're doing, what I'm doing also. Providing resources, we are in what's called Work Package 5. So we're providing basically Embassy as a playground to life science demonstrators. And we're trying to make sure life sciences are there, are represented, and they will be ready for it. A very tricky bit because some politics in it. So summing up, because I think we're running out of time, are we? Yeah, more or less. Well, my voice is running out. The science take-home messages. Better take a sip of water before. So what we learn and what we're basically saying across the EBI now is, if you are building something new from scratch, a new pipeline that didn't exist before, please keep clouds in mind, because you will likely be running it in clouds, and you better be prepared for it. If you're refactoring a pipeline, the kind of stuff that has been running in your cluster again for the last 5 years, try to build a normal pipeline, something that can jump around, flexible, put variables everywhere, because you want to change the behavior of the pipeline depending where it's running. You can build yourself a playground the way we did with OpenLava and the ganglia monitoring. We're actually upgrading that monitoring to be even more precise. You can monitor it, see where the problems are, then iterate, go on and optimize. You want to close that gap we saw before. The cloud can be a very cool playground. Do it at a small scale in the beginning, because otherwise you will be paying for all those lost resources, so the bill can be funny. Don't do network testing in the cloud, by the way. I did it. It was a £4,000 bill. Again, you need to try. We paid for you, so it's fine. Once you're up there, have fun, because it gives you total flexibility in what you can do. Okay? And again, all of this to say that clouds can be very cool, but you need to be ready for it. Moving data is still a big issue, but help is on the way. The data transparency layer we were talking about before, some providers are working on this. Depending on the scale you need to achieve, there are different ways. Cache everything in as an object in an object store possibility. Just send the files in before, then you can pull from the object storage, which is actually much faster than pulling from the network. Cache your data back again, the results in the object storage, and then pull them back. And this has the advantage that you don't need to have a full cluster waiting for the data to be copied across. Just you can copy to the object storage, you don't need VMs there. Do whatever you need to do and then sign back. Networks will be fundamental in any case, because you need to have a wire to get to the cloud. So the reality is, for at least AWS and GCP, if you are an educational customer, there are fee waivers for networks, so for the egress that you normally pay. So if you want to do something, have a look at those, because for AWS, I think up to 15 of your bill, if it is that's egress, you can basically don't pay it. And then Google has a similar thing. Something we're trying to do with Elix Nebula through the Giant. You know what Giant is? Okay, well, Giant is basically the federation, the network, the university networks, the research network across Europe. It's basically saying, okay, all the traffic that goes to you, cloud provider, that comes through a Giant network and goes out to Giant, since it's paid by somebody else, Giant, you shouldn't charge for it. Where all of this will lead us. So building infrastructure on top of infrastructure as a service is becoming commodity, right? There are all the tools out there to do it. Building and adaptive pipelines for the cloud is not, it will require specific investment, because it will take time. You need money to do it. And it also requires specific training. Again, today is a good example. When you will eventually have your hands on this presentation, there is a small link here. This is actually the link to the material we're using at the EBI to do ResOps training. Have a look. Feedback is very welcome. We need to build common knowledge and share it, because that's what we're trying to do, right? We need to understand how science can run, well, bioinformatics can run in the cloud in an efficient way, and then share it. Hopefully, initiatives like Elix Nebula and European Open Science Pilot or European Open Science, that's it, will ease the boarding process. And one day, everything will be hopefully easy at one point. So one last experiment. I'll give you a minute to read this and tell me how many of those you have. How many of those you are happy to build? Okay, raise your hand if you have all 4. Okay, 3, 2. Okay, now of course you are happy to some extent buy into the other ones you don't have. Good. We're actually hiring. So if you want to do DevOps or ResOps at the EBI, please go to that short link. The deadline is the 9th of June. This will be about supporting the pan-prostate project at the EBI using the Embassy Cloud, which is actually a very cool thing. So it's pan-cancer done for the prostate cancer. Thanks. The short link is there.